All right, guys. So, welcome back. Good to see you. So yesterday we did some practice, right? Hopefully you're checking your answers as you're going through that. And again, I mean, I know we don't have time in class to go through some of those answers and questions, but come see me. That's what I'm here for, to help you out. Reminder also that we'll have graded homework number 2. That's due Friday. Okay, make sure you're going through that today. We're going to be covering the rest of it. And then there is a test next Wednesday. So not this Wednesday, but next Wednesday we'll have our first Unit 1 exam. I'll have the review put online tomorrow, so you can kind of see what to expect. Okay? So, without further ado, let's get back into it. Today, we're going to talk about functions and relations. We've done that before in Algebra 2, so we're just going to revisit it, give you a couple new vocab terms. So our objectives: determine whether a relation is a function. Then we're going to apply function notation, determine x and y intercepts of a function, defined by y equals f of x, determine the domain and range of a function, and interpret a function graphically. Okay, so we're going to tackle all of that in this lesson. So let's do that. Let's start with the definition. So we have here a set of ordered pairs. So that's our x, y's. Is called a relation. And x and y. Okay, so relations are just all the x, y ordered pairs that exist in the real number system. The set of x values in the ordered pairs is called the domain of the relation. The set of y values in the ordered pairs is called the range of the relation. Okay? Again, just common knowledge that we know in the past, just rewriting it. So I have a little example here. So the table shows stock prices for Google at the end of each month from August of 2004 to February of 2005. Okay, and just a little small note for those of you who are financial people, this is adjusted for dividends and splits. Okay, not that you have to do much for it, it's already accounted for in the stock price. All right, so I'm going to put it over here. So this is a long time ago. These prices were up a bit, but kind of gives you something to think about with how far Google has come along. There we go. See, those are all the closing prices for stock, starting with month 8, which is our August. And then at the end, month 2 would be February, which is a closing price of 185.18. Okay? Imagine people investing into Google that early and seeing what it's all about. They're doing pretty good with it right now. Okay, so part A. We wanted to write a set of ordered pairs relation in the table. Okay? So remember, if you go back to our definition, a relation is just any set of ordered pairs. Well, looking at that table, there's ordered pairs in there if I had to graph them on an XY grid. So here we go. So we're just going to get 8, let's see, 102.37. They get paired up together. And again, I'm just going to continue to list the rest of them. So it'd be 9, 129.60, 10, 190.64. I'm out of space. Let's see, 11, 181.98. 12, 192.79. 187.99. And the last one, 2, 185.18. There we go. And the set notation there. Okay? So all those ordered pairs is a relation, and it defines this data table as we see. Okay. Next, part B. What is the domain? Okay. Well, taking a look at it, my domain, if I look at what it's defined as over there, it's all the x values in the ordered pairs. Okay. So that's going to be the following. I get this question asked a lot, like, does it matter the order? Technically, it doesn't. It is nice to write it in an order that is like least to greatest. I'm writing it as it appears in the table. So I'm not really too picky with how you write that. The range, based on the description, are all the y coordinates, right? Okay, so that's going to be this whole column. So we just took like a real world application and figured out how, in our realm, how those definitions apply to it. I forget what the textbook gave you, but I was like, let me get you something that's a little bit, I think, more interesting. So stock prices of Google, that's a little interesting. Okay, so there we go. Just basic definitions. So let's continue. So given a relation in x and y, say that y is a function of x. That's an important phrase. If for each value of x in the domain, there is exactly one value of y in the range. So I'm going to underline that part. Exactly one value of y in the range. Okay? So this is our definition of a function. Now, why does that matter in the math realm? Well, think about something for a second. That 8 in that table, that 8 represents the month of August in the closing price for stock, which is $102.37, okay? Is there another month of August that has a different closing price for Google? No, right? It doesn't exist. It doesn't make sense. You can't have two different closing prices for the month of August for Google, okay? So that's what this is telling us. This is telling us that, hey, if you want to look at a real-world application, we got to make sure that we don't have values like that, okay? So it's kind of just, narrowing down all those relations that exist in the world, okay? So all the relations that match this definition, we call them functions. Let's look at an example. Let's say I gave you this relation. finite amount of coordinate pairs there for this relation here, okay? And based off the definition, can this be a function? Okay, what do you think? Yay or nay on that one? Some people are shaking their heads no, and guess what? I agree, okay? What number, what domain value is causing some issues for us?
-1.
-1? Okay, why would you agree?
I do have a question, so
Yeah.
there's a math.
That's okay.
So the 1 and the 2 after 12,
Yes.
January, February, after December,
Correct.
is the 1 and the 2 going to change our data or anything? I know you said order doesn't matter if there was a previous 1 and 2. So would it be 13, 14 if there was already a 1?
Oh, so you're saying like if I went further in this year, is the 1 and 2 going to change anything?
Yeah.
That's a good question. If I was constructing the data table, I would probably either have a break here, indicating like, hey, this is only 2000, what was it, 4? This is only 2004s. Or just some other notation there just to indicate that.
Okay,
Yeah.
I was just confused because you said order didn't matter, but I
Mhm.
was assuming.
I mean, here's what I could do. I could say from August of 2004 onward for the next like 13, 14 months. And I could outline it that way. You know, this is month 13, this is month 14. But no, it's a good question. Yeah, absolutely. Okay, so this here and this here, yeah. No bueno. Okay, that's not good. It violates that rule right here. So therefore we could say the relation is not a function. Okay? Not that we're excited about it, but the exclamation mark really just kind of cements it, right? It's almost like you're yelling at someone like, no, that's not a relation, or that's not a function. So I'll put y next to it. So that's when x equals -1. There are two different y values, y equals 2, and y equals none. Okay? So that's the reason why it doesn't work. So let's try another one. Okay, let's look at this relation. And again, we're just looking at how this violates the definitions. Where you got to look at the domain. So is there anything here that's saying that's not a function? No, right? Everything works out. 20 only appears once, -4, 3, 11, and 0. They all appear once, so we're good. So this is going to be a function. So we could say here the relation is a function. Okay? By the way, it doesn't matter that the output 9, like this y value 9, got matched up twice. That's okay. Okay? Look, go back to this example. Could you have 2 months with the same closing price? That could happen. Probably not, but that could happen in this case. So that's all right. Alrighty. Here's where me and the textbook kind of split ways a little bit. So I want to introduce you to some terms. Okay, so I have another set of definitions I want to show you. I don't know what your future plans in mathematics are, but there are other ways to define functions, and we know these from Algebra 2. Remember 1-to-1 and on-to, those functions? So let's reintroduce that. But I'm also going to give you different terms that represent that, okay? Because these are terms that you would see in the future if you do continue with math. So here we go. If a relation is a function, but has the same y value paired with 2 different x values, we call the function surjective or onto. Okay, so we've heard the words onto function before. I'm just throwing in a new vocab term, so surjective is something that you might see, and that is the same thing as onto. Okay? So, same y value paired up with two different x values. So that means this guy over here would be surjective, because 9 got paired up twice, right? So that's a good example of it. Otherwise, the function is called injective or one-to-one. Okay? So if you have no duplicate y values, they don't exist, then that must be a one-to-one. Okay, that means every y value is unique. Okay? If a function is both one-to-one and onto, then we call it bijective. Okay? So if it's both, like, well, let's use this example over here as a guide. Let's change that to a 7. So notice every y value is unique, right? You don't see duplicates. So that is injective. It's one-to-one. Now notice that every y value is being paired up. So therefore it's surjective, it's onto. So because it satisfies both, we can call it bijective. Okay? All right. Any questions on that? So like I said, we did talk about these last year. We just never talked about those terms paired up with it. Yes?
What if the function is neither?
Say it again.
What if the function is neither? Because, for example, a set in which one output value is shared by two input values, or one range value is shared by two domain values, but not all of the range values are paired with the domain value.
Okay, so if that's the case, then it's going to be a one-to-one then, because everything's still unique.
Okay.
If there's nothing paired up with it, that's okay.
Well, I meant if two domain values go to the same range value, but at the same time there is one range value that is paired up with nothing.
That's paired up with nothing. Okay, so then that wouldn't be a onto case because there's y values not being paired up at all.
Yeah.
Okay,
But
but
it's not one-to-one either, is it?
true. However, there's not really a situation where that will occur, where you have a y value not paired up. So here's what that's saying. You're saying that you're plugging nothing in and you're getting an answer. You know what I mean? That's like saying, hey, I got a closing price of $200, but I don't know what month did that. You got to know what month did that to get the output.
Okay.
Does that make sense?
So it's not even worth considering.
Right. Yeah, because in terms of application, that doesn't really connect with this at all.
All right.
Okay. Yeah. Anything else? All right. Let's talk about the vertical line test. A lot of vocab here at the beginning, but we'll start applying. We'll actually get some examples in. More examples on what that is. So consider a relation defined by a set of points x, y, graphed on a rectangular coordinate system. A little shout out to Descartes, right? Because we talked about Descartes in the last lesson. He's the one who started us with this rectangular coordinate system. The graph defines y as a function of x if no vertical line intersects I'm gonna spell that right. The graph in more than one point. Okay. Another concept we talked about in the past, vertical line tests. Okay, but we're gonna do some examples underneath it. That way you can kind of see it applied in action. So I got some graphs for you. Here we're gonna determine if the relation defines y as a function of x. I know it's hard for you to copy things down when I'm in the way. I'll be moving soon. Hold on. There we go. Okay, so we have 3 graphs there. We're gonna see which one represents a function and which one doesn't. So look at the first graph, kind of wonky, okay? We'll be seeing graphs like this in the future where, you know, we have different things happening in the middle with endpoints going either up or down or vice versa. But if I were to draw a vertical line at any of these spots, it's only gonna hit the function, or the relation I should say at the time, at one spot. So this would be yes, okay, passes the vertical line test. I'm going to abbreviate it, BLT. We'll say yes, passes the vertical line test. Okay, so it's a function. Okay, B, we can see clearly that would not be a function. Okay, that's a circle. So no matter where I draw it, those two are not going to work. So this would be no. Okay, it fails the vertical line test. Not good. Now, what about C? Bless you. Okay, we talked about piecewise functions in the past. What do you think? Would that be a function? I'm drawing on myself. What do you think?
Yeah.
It will be, right? And honestly, it's this guy right here, right? This is the, what the heck's going on? So if you remember, okay, the open dot means I don't include it at this spot, but this says, oh yeah, do include it over here. So because only one of these are filled, you're good to go. So this one would be a yes. Passes, okay, vertical line test. All right. So it looks kind of weird, because think about it. Whatever this x value is, let's say the x value is 2, the output is not this guy, the output's this guy. So it's like a jump, is what happens there. And yeah, we'll see those as well in the future. Okay? Alrighty, so any questions with that? Think we're doing good? All right, let's talk about mappings. So a relation can also be defined by a figure, okay, showing a mapping between x and y. And a lot of times mappings can help us to determine a lot of things in mathematics, okay? If you ever take an abstract algebra course, we'll talk about like isomorphisms and homomorphisms, and those things, it helps to have a mapping just to determine if those things exist. So these are good things to have. And let me just give you a solid example underneath it. Let's say I had this relation. So something simple, right? Just 3 points in this relation, okay? How can I make a mapping? Well, you make two pretty much ovals in a way. Your first oval is your domain, okay? So this is your domain. That's your x values. So that's gonna be 1, 3, and 5. Over here is your range, that's your y values. That's gonna be 2, 4, and 6, okay? So you separate them, and then you draw arrows from your domain to your range that match here. So 1 is paired up with 2, so I'll put an arrow from 1 to 2. 3 matches with 4. 5 matches with 6. There we go. Okay, so that's just what a mapping is. Now we can use those very quickly to determine if something's a function. We can use it to determine a type of function. Okay, is it injective, is it surjective? So let's see how this works. Let's try an example. Determine if the relation defines y as a function of x. So those are two examples there. Try to use a different color so you can see the mapping a little bit better. All right. So, looking at the mapping, what do you think? Function or not a function? So I guess some people shaking their heads no. Yeah, it's not a function. And the reason why, well, let me ask you, what do you think? What's causing issues here? Why is it not a function? It's the 0, right? Yeah, 0's getting paired up twice. So this input has 2 different outputs there. I don't think orange is going to show well. Let's do pink. There we go. I'll put pink right there. Yeah, that's the troublemaker, right? Okay. So this would be not a function. I guess we'll continue with the exclamation mark. See, when you read back through your notes, you're going to be like, man, why am I shouting all the time? We don't know. We have no idea. Okay, next. This one here. Now, immediately, it might not be apparent, right? You might look at it and like, I don't know if it's a function or not. Well, let's graph it. I think graphing it could help, because then we can use what? The vertical line test? That's probably the fastest way. So I'm going to solve for y. So I'm going to take the square root to both sides. So this would be plus or minus the square root of x plus 1. Okay? Now, if you remember your transformations from last year, that's shifting the function left or right. Which way? Left. Okay, it's going to be left 1. And then square roots, it's just a curve above. But I got a negative there, so it's going to reflect it. So I'm going to have a curve underneath it. It's going to look like this. Okay? Now, is that a function? No. So this one would be, again, not a function. And our proof is that it fails the vertical line test. Okay? Doesn't work. Honestly, I mean, I think graphing's probably the fastest way to see if something's a function or not. I mean, you could look at an XY table, but you might be there for a while depending on what the function is. All right, so that takes care of that. Let's talk about function notation. So when a function is defined by an equation like y equals x plus 4, we often will use function notation. So y equals x plus 4 can be written as, so I'll step back here. Okay, so y equals x plus 4, that's a line. Lines are functions, passes the vertical line test. So because of that, we might rewrite it a little bit differently. Okay, we're gonna swap out y and replace it with something else. Okay, so we're gonna replace it with, well, it doesn't matter. F's the most common way to replace it, okay? And then parentheses is the variable we use that's in the equation, okay? So let's talk about this just for a little bit here. So what this is telling me is, and put it this way, you're telling the reader that this is a function, right? This is how you're gonna tell him. So you're gonna take this guy, oh man, I like blue. Darn it. Well, hey, we got more. Well, nah, yeah, I don't know. Anyway, okay, so we're swapping that out, and we're gonna replace it with a letter. Doesn't matter what the letter is, F is the most common letter. So this is the function name. Okay, you know how X, the most common variable, F is for functions. And then here it's the variable that is seen in the equation. In this case, it's X. It could be any variable, but that's what that is. All right? So we're just swapping things out. Now to read this, which you guys have been told in the past, you read it as f of x is equal to x plus 4. So here it is. You call it f of x. Okay? So we've used that notation so many times last year. Here we go. Let's try an example. So we're going to evaluate the function defined by h of x equals absolute value of x minus 4 for the given values of x. Okay. So let's just try just a normal number example before we put like other variables involved, which we will. Okay. Now again, I mean, just in case if you need a refresher, I'll put it on this board here. So if you look at the first one, okay, h of 5, that's telling me that 5 has to get plugged into h, right? So h has the variable x, so you're plugging 5 in for x in this equation. So it's like me saying this, if this was y equals absolute value of x minus 4, an absolute value, I say let like x be 5, you would do y equals 5 minus 4, right, in the absolute value. That's just what this is saying, right? Except instead of y, I got h. So here we go. So h of 5 is equal to 5 minus 4 in the absolute values. We'll just simplify it in one step. So that's a 1, absolute value of 1 is 1. So there's my final answer, okay? So So again, what this is telling me is that if we plug in 5 into function h, the output will be 1. Okay? Which is kind of convenient because you're getting everything in that one statement. I'm telling you what equation we're using, what I'm plugging into it, and what the output is. In this situation over here, I have it kind of scattered. Like once I'm done with this, I get y equals 1. But again, it's down here, then what did I plug in for x? So we're just kind of condensing it all into one statement there. Okay, last one over here. I'm going to plug -7 in. Okay, following the same rules and guidelines. So that would be a -11. Absolute value -11 is just 11. And there we go. Okay, all finished with that. So let's try another example, except with variables. Okay, so let's do that next. Evaluate the function. Defined by f of x equals 2x squared plus 1 for the given values of x. When you see variables being swapped out for other variables, that's where it could play tricks with your mind. But if you like to highlight or underline, I mean, this might help out as well. So what this is telling me to do here is plug this into f wherever you see the variable x. So x squared's coming out, that's going in its place. But be careful. This says whatever I plug in for x, I have to square it. I know that's already squared already, but that's okay, we're going to do it again. So f of b squared equals 2b squared raised to the second power plus 1. Okay? So again, you're just swapping out the variable, not the whole thing. So then, to simplify, so this will be b to the 4th with 2. So 2b to the 4th plus 1. This is not done. That's it. I can't go any further with that. Can I go 2 for 2? Nope, I can't go 2 for 2. Darn. Thank you. That's a sympathy point, right? It still gets in. All right, over here, same thing. I'm going to take x out and put this directly in its place. Okay, so we get something like that. Now again, I have to expand this guy. So let's go ahead and do that. So 2 times, now I'm going to kind of shortcut it. So we're going to raise the second one. And then you can multiply these together, you get negative AB. Double it, so it'd be minus 2AB. And then square the last one. Okay, so let me just put it up here. So what did I do? I just multiplied this a little bit quickly. Just a little bit quicker than usual, okay? And talked about it briefly in the past, but so now we have to multiply by 2. So this would be 2a squared minus 4ab plus 2b squared and then plus 1. And we're done. There's really nothing more that I could do with that, unfortunately. Until they tell me what the other variables are, I can't go any further. Okay? All right. Doing pretty good. So now we're going to talk about intercepts, and then the rest of it is kind of pushed together, the last 2 objectives. Let's do that next. Okay. Finding intercepts. given a function defined by y equals f of x, the x-intercepts are the real solutions to the equation f of x equals 0. Which we already know that anytime the graph crosses the x-axis, those are real solutions. If it doesn't cross the x-axis, then we have imaginary or complex solutions there. The y-intercepts is given by f of 0. Okay? Now, we know what a y-intercept is. We know that we would have to plug in 0 for x to do that. I'm doing the same thing here, just with function notation. This says plug 0 in for x, whatever the equation for f is, right? This here says, okay, anywhere where y is 0, because remember, f of x is y. So wherever y is 0, that's the x-intercepts. Okay, so let's do an example. Find the x and y intercepts of the function defined by f of x equals x squared plus 5x. Okay. So I'll just separate it. So I'll put here x-intercepts. Could be 1, could be more than 1, so I'll just put that in parentheses. Okay, so the x-intercept is when y is 0, right? So I'm going to put 0 in this place. 0 equals x squared plus 5x. Solving it, which we've done many times, I'm going to go ahead and factor an x out. I get x plus 5 in parentheses. And then we apply the 0 product property, so x could be 0. And if I set that equal to 0, I get x equals -5. So my two x-intercepts, and please, it's easy to do. Like when you solve for x, it's always nice, and you're like, oh, I'm done. But it is an intercept. So you want to make sure you write them as points. Okay, so my intercepts would be 0, 0, and -5, 0. So that means it crosses the origin. Okay, which is probably meaning that's the y-intercept as well. But let's solve it just to be sure. So y-intercepts are just intercept. So we have f of 0 I'm going to plug in. So I'm going to take the x's out. I'm going to plug zeros in for it. Which, again, it's just like me doing it with a normal type of equation. It's just with function stuff. So this will just be 0. So yeah, my y-intercept is at 0, 0. And you can always check, you know, you can graph it on your calculators and see, does it actually work? And it does. All right. Let's talk about domain and range. All right. And stop. Surprised, aren't you? The past Mr. McCullough is going to make a mistake around this point in the lesson. And he did correct it for his students, but I got to correct it for the video. So it wouldn't be proper for me just to correct it for my students and not for the video. And hey, math people, we make mistakes as well, right? So I want to make sure I do this correctly. Even though it was written correctly on my paper and my notes, but my brain, as I was writing on the board, flipped some things around. So let's continue with this lesson. So one of the things we're going to start talking about is domain and range of a function. Okay, it still follows the pattern of a domain and range of a relation. So given a relation defining y as a function of x, the domain is the set of x values in the function, and the range is the set of y values in the function. So again, nothing changing. In some cases, there may be restrictions. So if we have f of x equals x squared plus 2, for x is greater than or equal to 0, I'm right here restricting my domain. Now you might ask, okay, why restrict the domain? What's the big deal with that? Well, when we talk about inverses, it's actually pretty critical that we restrict the domain when it comes to inverses. So, new lesson in the future, we'll address it. So if I had this example right here, so I have a graph, I did put some of the numbers here, that way you can kind of graph it yourself, make it a little bit easier for you. And let's say that my question is determine the domain and range of the function below. Okay, so let's talk about domain. Again, it's all the x values that we see in this. And notice that -4 is the last x value that's being used. And then it hits 1, but it keeps going on infinitely. And the way I drew it, I do apologize, it looks like I just drew a straight line. It will eventually start curving in this direction right here, okay? So again, I just apologize. I don't want you to feel like, you know, it's just a vertical. It doesn't. So it will encounter all of the x values here, just anything after -4, not including it. So my domain would be -4, infinity. Now, the range, okay? Let's talk about that for instance. So this is the largest y value that I have for this function, and then everything beneath it. So -infinity, because I'm including all these values, because it goes to -infinity, and 5, bracket, because I want to include the 5 in that case, okay? So there's an interval notation example of domain and range of a function that's graphed for us. All right, so let's go ahead and take a look at this guy over here. So write the domain of each function in interval notation. Now when you have fractions, the one thing you want to consider is what would make the denominator 0, okay? Because if that's the case, it's undefined, you know, no bueno, can't have it. So I have a quadratic here, and that's okay, we can mess with quadratics. I'm going to set this equal to 0 to find the two x values that will make it undefined. I kind of got lucky here. I can factor this. So this factors to x plus 3 and x plus 2. Set both equal to 0. And then we get x to be a -3 and x to be a -2. So again, that's where things go bumpy with this function here. So what do I do now? Well, I don't want to include those guys. Okay, that's the important thing. So starting with -infinity all the way to -3, I want all those values but not including it. Okay, union with -3 all the way to -2, not including them. Union with anything from -2 all the way to positive infinity. Okay, all of those values would be acceptable. Okay, so this is my domain right there. Now looking at part B, that's a square root, and we don't want negatives under a square root. It's okay to be 0, but I don't want any negatives. I'm going to write an inequality to help me find the domain for this guy. Okay? So, solving it, we get 5a greater than or equal to 4, and then a must be greater than or equal to 4/5. So, my domain for this guy, okay, I want to include the 4/5 bracket, and then anything beyond is a positive infinity. Okay, so there's my answer for this function there. Those are all my domain values. So as you can see, we have two very diverse answers. One that's pretty straightforward, another one that we had a couple unions to put all the domains together. All right, let me just push this more towards the center so we can see it. Last example, now I have this graph. I'm trying to get creative with these graphs. Kind of looked like a smiley face, but then I kind of dipped it down, so I guess it's a little bit of a frowny face. But anyway, I want to answer the following questions. There we go. So first it says determine f of 6. And by the way, the graph, I try to put some key points on the grid. That way you're able to graph it yourself, make it accurate in your notes. This is a 12 by 12 grid, by the way. So I have some critical points on here. Now they want to know what happens at f of 6. In other words, if I plug 6 into f, what's my output? Well, if I go here, okay, that's what 6 is, so what's my output going to be? 11. So this is equal to 11 then. Okay. Next one, find all x values for which f of x is 0. Now remember, these are equivalent to each other. So when do we see y to be 0? Well, there's only one spot here. okay? So this is when x equals 9. So that's when we actually see it. We don't see it anywhere else. If I had another part of the graph that hits the x-axis, then that's another spot that I can include for that answer. But unfortunately, that's it. Okay, next, find all x for which f of x is 10. Okay, so again, what we're looking for here is when is my y value 10? Okay, and what x value gives me that? Well, I have a range of values, don't I? Okay, so if you take a look, we have this guy all the way to this guy. So from -12 to -7. That's where we see y to be 10. So I have an interval here. So anywhere from -12, including it, all the way to -7, also including it. That's where we see the y values to be 10. Okay, part D, determine the domain of f. So that's your x values. So notice, this is my least x value, which is -12. And if I go to the right, I can see that after 9, it still continues. So all these other x values are going to work. So anything from -12 to infinity. -12 being the lowest x value, and then everything beyond it. Okay, and the last one, the range value. Okay, well, the range of this is the highest y value or lowest y value, and anything beyond it. So let's see, I have 11, I'll just put a little circle there. So that right there is my largest y value. And then anything beneath it's going to get picked because this line continues. So therefore, -infinity all the way to 11, okay, is where it's going to end for me. So there we go. Okay, that is some functions and relations. A little bit of old, a little bit of new, kind of a review of everything. But anyway, I think we're good to go. So, hope you're having a good day, and I'll see you in the next lesson video.